Bismillah ar-Rahman ar-Rahim. Now we continue with what Dr. Salim has done in terms of kinetic theory of gases. Remember that Dr. Salim has showed you that average kinetic energy for one molecule. We're talking about translational kinetic energy here. So we are assuming that we're dealing with monatomic gases. A gas is monatomic, means you have one atom per molecule. One atom per molecule. I can give you an example. All the noble gases are monatomic gases. Noble gases such as helium, argon, and so on, and xenon, and so on. He showed that the average kinetic energy for one molecule, okay, the average kinetic energy, K average, was given by 3/2 kT, where K is Boltzmann constant. Actually, this 3/2 kT is coming. I can explain it to you. Actually, these are the 3 degrees of freedom, because this molecule is moving. It is free to move in 3 dimensions. Okay, we're talking about 3 dimensions, X, Y, Z. Okay, so you have half kT for the first dimension along the X-axis, plus half kT along the y-axis, plus half kT along the z-axis, and this will give you 3/2 kT. That's the translational kinetic energy on the average per molecule. That's the x-axis here, that's the y-axis, and this is the z-axis. We say this the equipartition of energy. Okay, so energy is divided equally in the 3 dimensions, and this is what gives you the 3/2 kT. Now let's go to for a gas of n molecules. Now we have a gas of n molecules. We don't have only a gas with 1 molecule like here. We have n molecules. You expect that the average kinetic energy in this case will be 3/2 n number of molecules, kT. Now remember that nk was shown by Dr. Salim previously at nk is equal to nr, where n is number of moles and r is ideal gas constant, and you get this equation here. So the average kinetic energy for n molecules, of course, is the number of moles, number of moles here. Okay, so, and this is the ideal gas constant R, and T is the temperature in Kelvin. Very important, the temperature in Kelvin. And we notice that the average kinetic energy for the gas molecules, which are n of them, n molecules, is 3/2 n number of moles, R the ideal gas constant, T the temperature in Kelvin. This is a very important equation here. Let's write it again. Average kinetic energy 3/2 n R T, and this is for n molecule. We're talking about translation here. These are for monatomic gases, 1 atom per molecule. Okay, we call them monatomic gases. Okay, when we'll see later diatomic gases, things will be different. Okay, so this is the average kinetic energy. It turns out that this is remember we talked about something called the internal energy of a gas. Okay, we talked about the internal energy. So let's relate to the internal energy of a gas. Internal energy. When these molecules are moving inside the gas, this is the kinetic energy, the average kinetic energy for this. Actually, this kinetic energy, which is all the molecules which are moving in the gas, actually they are the internal energy of the gas. So the internal energy of the gas, molecules energy is K average for these molecules. Okay, so E internal, remember we write E internal in the previous chapters. E internal is actually equal to K average, which is equal to 3/2 nRT, right? So nRT, that's the internal energy. Let me go to a PV diagram and show you. This is a PV diagram. Okay, and if you take a state here, a gas in a state I here, okay, at this location here, it has a pressure, it has a volume, it has a temperature. Let's say this is the T initial. Okay, so the gas in this at this state, it has an internal energy. okay? And that internal energy in this state is actually 3 over 2 and RT initial, okay? Temperature in this state. If you go to another state, now we go here to a final state where the temperature is T final here, it has another internal energy, the gas, okay? I call it E internal, here I put initial, here I put final, okay? It's 3 over 2 and R T final. So I can find the change in internal energy between these two states, okay? This is the state I and this is state F. I can find the change in internal energy. We call it delta E internal, okay? What is delta E internal? Is E internal final minus E internal initial, okay? So you have to subtract the final, the initial from the final. So what do you get? You get 3 over 2 and R delta T. That's the change in internal energy of the gas. This is very important result here. Eh? N is the number of moles. R is the ideal gas constant. Delta T here is a change in temperature between the two states. So a gas can have internal energy, and that energy, internal energy, what is it? Is the kinetic energy of these molecules which are moving in the gas, and they have a speed and so on. We call them the RMS speed, and this is a change in internal energy between these two states, okay? A state where temperature initial and the state where the temperature is final, and this delta T, of course, is T final minus T initial. Now, if the gas is heated, then delta T will be positive. So if you heat the gas, if T increases, okay? T increases, then delta T will be positive and delta T E internal will be positive. We say there's an increase in internal energy. If T decreases for the gas, T decreases, okay? If you decrease the temperature of the gas, then delta T will be what? Will be negative, and delta E internal will be negative also, okay? Will be negative, okay? So the change in internal energy, the sign of the change of the depend on the sign of delta T here. Here delta T doesn't have to be in Kelvin, by the way, because delta T in degrees Celsius or say Kelvin are the same. But delta T, but when you have a ratio of temperatures, make sure that you have to convert to Kelvin. Here you don't need to convert to Kelvin. It can be in degrees Celsius, it can be in Kelvin. They are the same. That's the change in internal energy for a monoatomic gas, okay? That's the change in internal energy for a monoatomic gas, 3 over 2 nR delta T. We notice something important here, that the internal energy of the gas depends on the temperature in Kelvin. Temperature here is in Kelvin. One other important feature about this I want to discuss now is as you go from this point to this point through this process, this is an expansion, by the way. As you can see, the volume has increased. You can go through this process number 1, or you can go through this process number 2, okay? Or you can go through this process here, all the way to here, number 3. As long as T initial and T final are the same, you notice that delta E internal is the same for all 3 processes. You have noticed that. So we say that the internal energy is a state function. What does it mean, the state function? It depends only on the initial and the final state. If the initial and the final state are the same, then delta E internal you go through any process, it will be the same. You notice that there's only delta T here, which is important. If T initial and T final are the same, you go through this process, or this process here, number 3. So delta E internal will be the same. Let me write down this information here. Delta E internal through process number 1 equal delta E internal through process number 2 equal delta E internal through process number 3. Any function which has this property is called the state function. Now let me go to talk about the heat. Dr. Salam has given you the work done for different processes. Let me now give you the heat done for different processes, okay? The heat Q. So I want to talk about the heat Q, okay? You can absorb heat. A gas can absorb heat or can lose heat. So if the heat is absorbed, it will be positive. If the heat is lost, it will be negative. So let's look at the heat Q for different processes. Let me first of all draw a PV diagram. And we said very important. We mentioned this in a previous video. I don't know if you remember it or not. That like work, the heat depends on the process. It depends not like the internal energy. The internal energy, if you take T initial, T final the same, it's path independent, but the heat is path dependent. So let me show you two processes here. This is an isothermal and another thermal here. Okay, these are at temperature T. This is at T plus delta T. Dr. Salim told you that as we go up, the temperature increases. So this is less temperature than this process here. Okay, and this is called the process, the isothermal, as you can see here. So if we go now from this point like this, or you go from this point like this, and calculate the heat, even though T initial and T final are the same for both, but Q is different because path dependent. This path is different from this path. So I call this one Q1 and I call this one Q2, and I'm going to show you that Q1 is different from Q2. That the internal energy was the same. Let me go back to the internal energy and mention something also here important. What happens if delta T is equal to 0? That's what kind of process where the temperature is constant? You have a process and the temperature is constant, delta T will be 0. It's the isothermal process, okay? So if you have here an isothermal process, you can see that delta T internal will be equal to what? Will be equal to 0 because isothermal temperature is constant. So delta T will be 0, and you have delta E internal equal to 0. This is important to point, okay? So let's go back to the heat here. Now, let me calculate the heat through process number 1 and the heat through process number 2 and see how what are the expression for the heat. Remember that Dr. Salim has showed you expression for the work for different processes. Now we are going to do the same thing for different for the heat Q. Okay. Let's go to Q1 let's go to Q2. Okay. Let's calculate Q2. First of all, the volume is constant here. Is iso. It's a constant volume process. You remember that a constant volume here. It has a name. Okay, we call it isochoric or isovolumetric process. Okay, and I want to find. Of course, I'm going to go to the most important equation, which is the delta E internal, which is equal to Q minus W. I'm going to use this equation here, and remember that the internal can also be expressed like this. Now we have two equations for the delta E internal. We have this one here, and we have this one here. Okay. Now, a constant volume process, the work is equal to 0, as was mentioned by Dr. Salim. You can see the process is there is no area under this line here. If there is no area under the curve, it means the work is 0. And also the volume is constant, so the work is integral of P dV, and dV is 0, so the work is 0. So how much is Q2 then, according to this equation here? Q2 will be equal to delta E internal, but delta E internal has only one equation, which is this one here. So this is 3/2 N R delta T, okay? So I'm going to group things together here. I'm going to put this 3/2 R together and N delta T, okay? Okay, so we continue now with the Q2. This is the heat for this process, constant volume. We reach to this point here, 3/2 R and delta T. This 3/2 R, I'm going to call it a C, specific heat, molar specific, molar specific heat. I'm going to put V here, CV, to distinguish it from the next C that we will see later, okay? CV, V, remember that we are doing a constant volume process, so we put V here, and R delta T. So this heat for Q2, for that process, is N CV delta T, okay? That's the heat during this process here. Now, in this case, where we are talking here, you see, the temperature has increased, delta T is positive, so Q2 will be positive. So this Q2 can be positive, so if delta T is positive, Q2 will be positive. If delta T is negative, Q2 will be negative. And remember that CV is equal to 3/2 R. This is a constant. And this is true for monatomic gases, such as helium, argon, xenon. This is the value for CV. Yeah? And actually, this value here, I can give it to you if if you do the multiplication. That value is exactly 12.5. Okay, 12.5, okay? 12.5 joules per mole Kelvin. Okay, now let's go to calculate the heat for the other process. For Q1, let's go for the other process. Q1. Let's go to Q1 now, okay? Q1 is a constant pressure process, constant pressure, okay? That's the pressure there is constant during the process, but the temperature and the volume are changing, okay? And this is an expression, you can see that. So again, I'm going to use Q1 will be delta E internal plus W, plus the work. You take the work to the other side, okay? And delta E internal, again, is the same expression, doesn't change, okay? It's the same one. The same one I used here because remember that delta T is the same for both of them. T initial and T final are the same for both processes. So it will be 3 over 2 or 3 over 2 N R delta T plus P delta V because the work will be the area here. It will be pressure P, the pressure P times delta V, the change in volume. It's the area under the curve, remember. But P delta V is equal, this one here is N R delta T. It was shown by Dr. Salam in the previous video, okay? So you have 3 over 2 N R delta T plus N R delta T. This gives you 5 over 2 N. Let me put R here, 5 over 2 R times N delta T. And this 5 over 2 R is going to be called CP, constant pressure, to distinguish it from this CV. This is it's called the molar specific heat. But this one is at constant volume, and this one is at constant pressure. And I can give you the value for CP. CP for monatomic gases is equal to, for monatomic gases, CP is 20.8, okay? This is 20.8 joules per mole Kelvin. That's the heat. Let me write it down here. Q1 is equal NCP delta T. So now you know how to find the change in internal energy for the gas. It's here, independent of the process. And then if you want the heat, it depends on the process. This is at constant volume, this is at constant pressure process. Let me show you now when you have the other processes, isothermal and adiabatic, and we close this video here, okay? Let me show you the 2 other processes. We do exactly like what Dr. Salam has done. He showed 4 processes, the work, and I'm going to show you the 4 processes, the work for the 4 processes. Let's now go to adiabatic process. For adiabatic process, we know that the heat is equal to what? 0. It means either one of the 2 things, okay? Either the system or our gas is isolated, okay? Or the process happens very fast. Very fast. The gas didn't have time to exchange heat. One of these, that's for the adiabatic. So we have, remember, I call this Q3, okay? Q3. Let me go to that's Q1 here for isobaric, Q2 for isochoric, Q3 for adiabatic, and let me go to isothermal and close, okay? For the isothermal process, remember the isothermal temperature is what? It's constant, So the temperature is constant. If you come here, you can notice that if the temperature is constant, delta E internal will be 0, okay? So, and we go to that equation here, delta E internal is equal to what? Q minus W. This is 0 here. It means that the Q, I'm going to call it Q4. Q4 is equal to the work. And remember, go back to the previous video and you see Dr. Salam has proved to you the work for isothermal process. It was N, R, T, ln of what? V final and V over V initial. That's the heat for adiabatic here. It is 0. And that's the heat for isothermal process. It's here. And those 2 are for the isochoric and isobaric processes. Let me now discuss. Up to now we have discussed the monatomic gases, where the molecule is made of 1 atom and it has only translations. And we have seen half kT for each degree of freedom, for each direction. So for three-dimensional motion, we have three directions. Now, so we have half kT for each direction, for each degree of freedom. Now let me go to a diatomic molecule. A diatomic molecule will be something like this, okay? Example will be hydrogen, OH2, O2, N2, okay? These are diatomic molecules, okay? So you have two atoms connected to each other like this, okay? And then this molecule can translate in three dimensions. So you have half kT, and half kT. That's 3 over 2 kT, okay? 3 over 2 kT. This is for translation. But also, this molecule can rotate. Because when you have one atom, the rotation has no, doesn't introduce any energy, okay? Because it's only one atom. But now, you can have two rotations. You can rotate about this axis, like this. So you have to add half kT for this rotation, and it can rotate about this axis, okay? An axis which is perpendicular. So another half kT, okay? Half kT. So how many of them I have now? I have 5 over 2 kT. That's for a diatomic molecule. So whenever you see 3 over 2 R, you change it into 5 over 2 R, okay? Now, so for diatomic molecules, okay, diatomic, so my CV, which was here for monatomic gas, was 3 over 2 R. Remember, you have to add R and another, you have to R here, okay? It becomes 5 over 2 R. 5 over 2 R, okay? And CP becomes 7 over 2 R. That's for diatomic molecules, okay? That's the CV and CP for diatomic molecules. Whenever you see CV here, if it is a diatomic molecule, this becomes 5 over 2 R instead of 3 over 2 R. Whenever you see a CP, that becomes 7 over 2 R instead of 5 over 2 R. That's for diatomic molecules. We have 2 degrees of freedom here. We have to add them because of the rotation of the molecule. Of course, we are not going to very high temperature where you have vibrations. You can also include vibrations, but we are not going to talk about vibration here. We talk only about rotation, about the axis of the axis. We have 2 rotations, and we add them to get the 5 over 2 R. So, if you want to summarize, for monatomic gas, CV is 3 over 2 R, and CP is 5 over 2 R. And for diatomic gas, CV is 5 over 2 R, and CP is 7 over 2 R. You notice something very important, or let's say CP minus CV is always equal to R. This is the relationship between CV and CP. So if you want to go from one to the other, you add R, okay? CP is always R, CV plus R. Thank you.